Hello, this is Mr. Yeager for chemistry, moving into our stoichiometry unit, which is one that everybody always talks about when they hear of chemistry in high school. And it's very similar to the mole unit. We're just kind of taking it another step. And so if you were good at the mole unit, this usually goes pretty well in addition, because we're just adding some additional steps to those mole calculations. But this is also where we are finally really getting into what chemists would do in terms of developing reactions and creating products and getting some good percent yield and all those things to determine how they put these reactions together. So this is a very, very important chemistry unit in terms of application of chemistry. So in this presentation, we are going through a bit. We are going to introduce what is stoichiometry, and we're going to start with basically 3 of the 4 type of stoichiometric calculations, and we'll kind of go through them. So you can see the title here is mole to mole and mole to mass. There'll be another presentation I'll be pulling up as well, because we're going to do mass to mole at least. But all these presentations, again, have been created by another excellent chemistry teacher that I work with, and then I just make the video. So here we go. All right, so stoichiometry itself is a way that we calculate the quantities that will be used and that are created or produced in a chemical reaction, okay? And we have to use the mole to figure this out, so we're using the prior unit. But what we're now bringing in is what the second point is. We're bringing back the chemical equations, the chemical reactions themselves. So this is again where we need to be able to identify compounds and possibly write out compounds, in addition to then writing a chemical reaction, balancing it, and then using that reaction to do some mole calculations, okay? I like the idea. This is kind of giving you some real-life application. Again, there's real-life application in chemistry, but the same idea goes with if you are somebody that likes to cook and you have to kind of adjust the ingredients, especially when there's more people. That's stoichiometry, really, all right, is what's being involved when you're going, hey, I need 4 servings of this, and now I need to get 8 servings. What do I need to do with all the ingredients? Double them so that I get the correct amount of stuff out, all right? So the first thing I had to introduce is something called mole ratio, okay? This is the only really new thing at the beginning of this new unit is this is the connection between the chemical equation and the math that we have been doing back in the mole unit, okay? The mole ratio is relating 2 different compounds and essentially how many moles of each are present in a compound, and we use the chemical equation to figure that out, okay? That becomes a conversion factor between moles of one type of compound to moles of a different type of compound. So this is the only conversion factor that allows you to switch compounds. Okay? In our prior unit on the mole, we stuck with one compound and then just changed it from mass to mole to liters to particles. We never had to change one compound into another compound. And since this is a chemical reaction, we have multiple compounds involved. And if I want to figure out if I put this much compound in, how much does this come out? How much does this other compound get produced? I need to use this thing called the mole ratio. Now, the chemical equation is so important because the coefficients in the chemical equation are the number of moles, and therefore help us get this conversion factor. So again, this changes based on the chemical reaction. This is also why it's so important to balance right, because if you don't balance right, the mole ratio is wrong, which means your problem is wrong. Okay? So it starts with balancing the equation. Okay? So I'm going to kind of show, it's immediately jumping into mole-to-mole problems. I'll get to that in a second. I just want to go over, let's figure out mole ratios. Like, let's say I give you an equation. I say, what's the mole ratio between 2 compounds? So if I look at this, I go, okay, here's my chemical equation. I need to balance it first. I have to make sure it's balanced. I can't, like, the formulas are right, but I got to balance this out. So I have one C, I have one C. I have 3 O's, I have 4 O's. All right? I'm going to come back to the O's in a moment just because there's multiple areas where there's O's. So I'm going to skip O and I'm going to go to LI instead. And I'll come back and make sure O is balanced. So I have 1 LI, I have 2 LI. So I'm going to put 2 right there now. Okay? I have 2 H's. Again, I'm skipping O for the moment. 2 H's, 2 H's. Look at this. I have 2 O's and I have, for a total, I have 4 O's on this side, 2 from each compound, and I have 3 plus 1. Hey, it's a good thing I skipped it and came back to it. My equation is now balanced. Okay? All right, so what would mole ratio be? So if I said, I want you to find the mole ratio of CO2 to H2O. And I say, please write the mole ratio for me for CO2 to H2O. Okay? What I do, and all I do, is I have my balanced equation and I just look at the coefficients in front of those 2 compounds, just those 2. Since there's no coefficient there, the assumption is that's 1. So my mole ratio between CO2 and H2O would be 1 mole of CO2 to 1 mole of H2O. And that's it. That's it. Okay? If I do, what's my mole ratio of CO2 to LiOH? I would do 1 mole of CO2 and 2 moles of LiOH. And ta-da! That's it. Okay? Where am I getting these numbers from? I'm getting them from the coefficients in the chemical equation. All right? That's it. So one more. Let's just make sure we really got it. What would, I'm going to give you the toughest one here, the mole ratio of LiOH to Li2CO3 be? All I do is I look at the coefficient. 2 moles, and it's moles. This is the unit. We got to be writing our unit, and I'm going to strongly encourage that you write the compound now with it. Some people are going to be like, oops, I'm sorry to make a mistake. Some people are going to be like, I don't want to write all that. Write it. What's the coefficient in front of LiCO3, Li2CO3? 1. And there's your mole ratio. Okay? And all I'm doing is whichever one I'm listing first is the one I'm putting on top, whichever one I'm listing second is on the bottom. I could technically flip it, but we do like to say I'm doing it from this one to this one, so write the first one on top, the second one on the bottom. All right. So now how do I get to using that? So here's our thing. So we already have it balanced. We know there's a 2 right here. And here's my question. How many moles of lithium hydroxide are required to react with 20 moles of CO2? The average amount exhaled by a person per day. That's great. I'm glad we have that last detail. It's really not that important. All right. So what I do with this, okay, is I recognize I always still start, just like I do with mole problems, whatever's given to me. So 20.0 moles of CO2. And I'm just doing my train tracks again. Okay? I can go from moles of one compound to moles of another compound using mole ratio. And I'll draw a little diagram out with this in a moment. I can change from one type of compound to another type using mole ratio. It's the only thing that helps me change. So I still use the same process, my mental process of going, in the next squares over, the bottom is what I'm coming from. I'm coming from moles of CO2. I'm going to moles of, what am I going to? Lithium hydroxide, LiOH. Okay? Again, we'd have to be able to recognize that's the one I'm looking for, lithium hydroxide, LiOH. All right. Finally, there can be something other than 1 in front of moles. When we did mole calculations and conversions, I said mole is always 1 when it was with a different unit. But when mole and mole are together, I'm using the mole ratio, which means where do I have to look? I have to look back at the reaction. What number is in front of LiOH? 2. What number is in front of CO2? 1. And I'm done. I'm going to cross out moles of CO2 on the top and on the bottom. I'm in what I'm looking for, moles of LiOH. And then I do what I do normally. Everything on top I multiply, everything on the bottom I divide. 20 times 2 is 40, but I need 3 sig figs because I'm using the original number. And 40 moles of LiOH is my final answer to that question. That's it. Okay? This is initially probably going to look fairly simple if you recognize what you're using. If you don't recognize what you're using, then yes, you're completely confused. All right? But you're going to see a lot of these calculations are very quick, very simple because we're using whole numbers. And then we figure out the sig figs, write the unit. Again, I would absolutely recommend that you write out the chemical. All right? So there we go. So again, where did the 2 and the 1 come from? They came from the balanced chemical reaction. So let's try another one. I don't know why we're sticking with lithium. All right, so Li plus O2 produces Li2O. I got to balance it. I have 1 Li, I have 2 Li, so I'm going to put a 2 there. I have 2 O's, I have 1 O. I need to put, not 2 there, I need to put a 2 on the other side. That now means I have 4 Li's, so I need to put a 4 here. So there's my balanced chemical reaction. What's the problem now saying? It says how many moles of lithium oxide, which is this, will form if 2 moles of lithium react. So I'm starting with 2.00 moles of lithium. I use what's given to me in the word problem. All right, I'm going from moles to moles. That's a one-step affair. I come from moles of lithium, I go to moles of lithium oxide. Where do I get my numbers from? In front of mole and mole together, I look at my chemical reaction. 2 is in front of Li2O, and 4 is in front of Li. I multiply everything across and I divide by everything on the bottom. So 2 times 2 is 4, divided by 4 is 1, but I need 3 sig figs, so 1.00 moles. I can cross out moles of Li, so I know I'm ending with Li2O. I use the coefficients from the chemical equation. Moles of lithium is on the bottom because it's what I'm coming from. Moles of Li2O is what I'm going to. There we go. All right. Maybe 2 more. How many moles of oxygen will result from the decomposition of 5.75 moles of peroxide? I need to balance this first. H2, 2 O's, or sorry, 2 H's, 2 H's. 2 O's, but I have 3 O's over here. I'm going to double this one because I need to get to 4. I can't get 3. I can't have an odd number. So I'm going to double that one, which now gives me 4 O's, but also 4 hydrogens. So then I put 2 there, and I'm all balanced. I'm starting with 5.75 moles of peroxide. Now this might be tough, and I think in an on-level class they would probably say, what is peroxide? We should be saying peroxide is H2O2. If you didn't know that, you could read for context and say result from the decomposition, this is the thing decomposing, all right, into oxygen. So 5.75 moles of H2O2. I'm coming from moles of H2O2, and the problem wants me to find moles of O2. O2 has a coefficient of 1. H2O2 has a coefficient of 2. So this is going to be 5.75 divided by 2. 5.75 divided by 2. And I get 2 points, and I'm going to round to 3 sig figs, 8 moles of O2. One more, if they have it. Okay. How many moles of ammonia? Ammonia is NH3. Solving for NH3 are produced with 0.6 moles of nitrogen, N2. 2 N's, 1 N, put a 2 there. 2 H's, 6 H's, put a 3 there. So I'm starting with 0.600 moles of N2. One of the problems I could see with any of these problems we're about to do, because all you're going to see is this get bigger, is that you just don't read the problem and you don't recognize what the numbers go with, 0.6 moles of nitrogen. I'm in moles of nitrogen, so that's what I'm coming from. I'm going to go to moles of ammonia, which is NH3. I look at the coefficients. Ammonia's 2, nitrogen's 1. I just ignore the 3. I don't care. That's not involved. The mole ratio is supposed to be between two elements, or two compounds. And 0.6 times 2 would be 1.2, but I need 3 sig figs. So 1.20 moles of NH3. And that's it. I think that's where I'm going to stop with this video, just so we don't make this really, really long. But that's basically what we're looking at. Oh, let me go ahead and point this out. What we have basically done so far, and this is something that's going to expand, and I guess I'll kind of preview the next thing, is we basically have been going from moles of one compound, CPD stands for compound, to moles of a second compound using the mole ratio as the conversion factor. If I want to change from moles of one compound to moles of another, I use the mole ratio. I have to be in the mole. Mole, again, guys, is going to be in the middle of all these problems. Okay? So, let's stop there and practice, and then we'll come back to additional problems in another type of, where we're just going to expand it by one. All right? Thank you very much.